Chapter 6, the normal distribution. The normal distribution is a bell-shaped distribution of continuous data. If you look at figure 1, you can see the bell-shaped curve. It also indicates that the mean, median, and mode are at the same spot. Now that does not mean that for a given set of data that have a normal distribution that the mean, the median, and the mode would be exactly the same value, because that will almost never happen. But theoretically, they're in about the same spot, so they should be very similar. If you look at the center, you notice there is a 0, and then going out in each direction we have 1s and -1s. The 0 in this case is the mean of the distribution for this particular example, and the standard deviation is equal to 1. So the distance between each of these sets of tick marks is 1 standard deviation. So you can see that the majority of the data in a normal distribution are within 3 standard deviations on the negative side and 3 standard deviations on the positive side, encompassing a total of 6 standard deviations. That does not mean that there would not be any values higher than or lower than those 3 standard deviations, but the bulk of the data are within those 3 standard deviations. Another way of looking at the graph with regard to the standard deviation is to note that the standard deviation is the point on the curve where it goes from convex to concave, meaning it's the point at which the graph goes from curving down to starting to curve up. And so that happens at the point of the standard deviation. Here we have a second example of a normal distribution. In figure 6.2, there is a histogram of 10,000 observations that were generated by the computer from a normal distribution with a mean of 0 and a standard deviation of 1. Very similar to the curve on the previous slide. But as you can see, if we look at the histogram with the individual bars, it does not have that perfect bell shape to it. There are some locations where the pattern is not exactly following that curve. But overall, you get the impression that a normal bell-shaped curve could overlay this histogram and give you that essential bell-shaped pattern. You can also see here some values that are actually beyond 3 standard deviations. This one is even beyond 4 standard deviations from the center. So there is potential for values to be beyond plus and minus 3 standard deviations, but you can see that the bulk of the data are within plus and minus 3 standard deviations of the mean. Here's another example of data that do not show a perfect normal distribution. So this is our final grades data, and you can see that, for example, right here, we don't have a bar that goes up as far as we might expect it to if this were a perfect normal distribution. But when we have a sort of a bell-shaped curve to our data, we tend to refer to it as having somewhat of a normal shape to it, even though it does not have that perfect bell-shaped curve. So the next thing we want to look at is finding proportions of the normal distribution. We want to do that because we often will have a big set of data where we want to know what is the proportion of individuals that are less than a certain amount or greater than a certain amount. And knowing that the data follow a bell-shaped pattern, a normal distribution, we can use the normal distribution calculator to approximate those values. So let's consider these 3 examples. For the first one, we indicate that we have a population with a mean of 0 and a standard deviation of 1. That is exactly what we have in this graph right here. A mean of 0, which is the center, and a standard deviation of 1, meaning that this distance here, this single standard deviation, has a distance of 1. So now what we want to find here can be written 2 different ways. We can write that as the proportion of individuals with scores less than 0, the other way we could write it is the probability of an individual obtaining a score less than 0. So in this first example, we're looking at a set of data that has already been collected, and we're wondering what the proportion of individuals are with scores less than 0. And in the second example, we're considering the probability of a future event and saying what is the probability of an individual having a future score that is less than 0. They're both essentially found the same way. We're going to get the same results. It's just two different ways of defining this same statement right here. So we're saying the probability or proportion of the individuals with scores less than 0. So x is considered our score. So if we look at our graph and we find where 0 is, it's right here in the middle. We're wanting to find the proportion of individuals less than 0. If you shade in the area of the graph that pertains to, that percentage of the graph that is shaded in is 50%. The proportion then would be written as 0.50. Let's look at the second example. In this case, we have a population with a mean of 5 and a standard deviation of 3. Here we have 0 as the mean and 1 as the standard deviation. We want to convert that so it looks more like our situation that we're dealing with. So for our population, we have a mean of 5, so 5 goes right there in the middle. We have a standard deviation of 3, which means that the distance between the mean and the first standard deviation is equal to 3. That also means that the distance between each consecutive standard deviation is also 3. So we have 5 as the mean. Then right here where we have the mean plus 1 standard deviation, where a standard deviation is 3, it's going to give us 8, because 5 plus 3 is 8. Then if we add another 3 to it, we have 11 and 14. Now if we subtract 3 from it, we have 2, minus 1, and minus 4. So this is the population setup for the second example. Now we're trying to find the probability of a future score that is less than 6, or the proportion of scores that are less than 6. So now we have 5 right here in the middle, and 6 is going to be somewhere right in here. So we are wanting to find the area. Sorry, that's not quite a straight line, but we're wanting to find the area that's shaded that is less than or equal to 6. And the less than or equal to part, it doesn't make much of a difference as far as whether you have less than or equal to or whether you have strictly less than. Because it's continuous data, it's going to give you the exact same answer. So in order to find this, we want to use StatCrunch. So if we go to StatCrunch and we select Stat and then Calculators and then Normal, it gives us the normal calculator for calculating proportions and values with regard to the normal distribution. So now we want to set up the situation that we have here with our population. You can see again, here we've got the 0 in the middle with the minus 1, minus 2, minus 3, and the positive 1, 2, and 3. And so this is the setup of the first situation, but that's not the population we have in the second situation. In the second situation, we have a mean of 5, so we'll plug in 5 here for the mean, and we have a standard deviation of 3, so we'll plug in a 3 for the standard deviation. Then, down here, we're looking at the direction of the arrow for the inequality sign, which is pointing to the left, or the less than or equal to, so that's what we have here. And we're wanting to find the probability of getting less than or equal to 6, or the proportion of values that are less than or equal to 6. Again, those are interchangeable. So that's the setup that we have. You can see that we're plugging in the numbers just as we see them here in the statement. We're putting those into the calculator. Now, if you had the variance instead of the standard deviation, then all you would do is take the square root of the variance and put it in here for the standard deviation. So now we click on compute and it will give us the answer. It shades in the area that is less than 6, okay? It shows us the setup that we have listed here in our graph below, which it has 5 in the middle and 2, -1, and -4, although it doesn't include all of those values here. But you can see that it set up the values appropriately as we would expect based on the mean and standard deviation that we provided. Then it shades in the area that is less than 6 so that we know we're getting the correct shaded in area. And then it gives us the probability that we asked for, which is the probability of an individual getting a score less than 6, which in this case is 0.6305587. So we could go over here to our answer and put 0.63. And you can tell that 0.63 makes sense as an answer because the area that's shaded in on the graph is about 63% of the graph. Now we want to look at the third situation, which again has a mean of 5 and a standard deviation of 3. But this time we're looking for the probability of an individual with a score greater than 6, or the proportion of scores that are greater than 6. So we have the same setup as we had before, with 5 as the mean and 3 as the standard deviation. So 8, 11, 14, and then we have 2, -1, and -4. So that's again the situation of our population, and we're highlighting the area from 6, but this time we're highlighting it on the upper end. So we're looking for values greater than or equal to 6 as opposed to less than or equal to 6. Well, there's a couple of different ways that you can solve this problem. One way is to just use StatCrunch. So again, we have a mean of 5 and a standard deviation of 3, and we have 6 here, but we're looking now at the inequality sign being in the opposite direction. And when we do that, we get an answer of 0.369 or 0.37, which is the area that is shaded into the right of 6 as opposed to what we had before, which was the area shaded into the left. So 0.37 is the result. Now the other way of looking at this is the fact that all of the area adds up to 1 or 100%. And so if we consider 63 as the area to the left of 6, then we could consider the area to the right of 6 to be everything but the 0.63. So 1, which is everything, minus 0.63 is going to equal 0.37, which is what we have right here. So the two different ways that we can compute that is we can subtract from 1 to get, if we have the left side of the graph shaded, to get the right side of the graph shaded, we subtract from 1. And also, if we have the right side of the graph shaded, we can get the left side of the graph shaded by subtracting from 1. The other way is just to do it in StatCrunch. The answers will be exactly the same. Standardizing scores is an effort to be able to compare scores that are on different scales. If we standardize them, then we can compare them apples to apples as opposed to apples to oranges. So, for example, consider our fictitious person Bob, whose statistics test score was 65%. The mean for that test was 55%, and the standard deviation of that test was 5%. If you can imagine, there are a whole bunch of test scores, and they form a distribution. And we can set that up just like we did on the previous slide, where we have a normal distribution curve, and we have the mean in the middle, and then 1, 2, 3 standard deviations, and 1, 2, 3 standard deviations out to either end. And we indicated that the mean score was 55%, so we could put that in the middle, and that the standard deviation was 5, which means that the distance from here to here is 5%. And so you can imagine that this first standard deviation, that is going to be 60%. Then we have 65%, 70%, and on the other end we have 50%, 45%, and 40%. So the majority of the scores, in fact, about 99% of the scores, are between 40% and 70%. That was a hard test. If we want to standardize Bob's test score, essentially what we're doing is taking out the scale so that it can be compared to another test score, say for a different exam. The way that we do that is by subtracting the mean from the test score and dividing by the standard deviation. When we do that, we get a score of 2 for Bob's test, meaning that Bob's test score is 2 standard deviations above the mean for that statistics test. If you look at our graph, you can see that that's actually true because we have the mean right here in the middle, and then we have plus 1 standard deviation here, and then plus 2 standard deviations here. Well, that plus 2 standard deviations is associated with 65%, which is what Bob got on his statistics test. That's his statistics test score. So you can see that his statistics test score is 2 standard deviations above the mean of 55%. Now let's suppose that Bob has a math test score of 80%, where the test mean was 70% and the standard deviation of the test scores was 10%. That gives us a different population setting because it was a different test that has different scores. So we no longer have a 55 in the middle, but we have a 70 in the middle. And the standard deviation is 10, so now we increase in increments of 10%. So we have 80%, 90%, 100%, and then on this side we have 60, 50, and 40. So the scores on the math test were much higher and more spread out than the scores on the statistics test. Now if we look at Bob's math test score relative to the other test scores in that test, now we can standardize Bob's test score by saying Z, which is the standardized test score, is equal to his score of 80, or 80%, minus the mean, which was 70, divided by the standard deviation, which is 10. And if we do that, we get 1 as the answer, which essentially means that Bob's score of 80% is 1 standard deviation above the class test score mean of 70%. So what it does is it gives us an indication of Bob's relative placement on each of these test scores relative to the other students in the class who took that same test. So the question asks, what was Bob's relative position on each test compared to the other students who took those tests, and on which test did he do better? So his relative position on the statistics test score is that his score is 2 standard deviations above the mean for the test scores in that class. And on the math test, Bob's score of 80% is 1 standard deviation above the mean of the scores on that test. Another way that you could write it out is to look at the percentages or the proportions. And so if we go to StatCrunch, we can set up the situation for Bob's statistics test by finding the mean of 55 and a standard deviation of 5, and then finding Bob's score of 65 and finding the proportion of scores that are higher than Bob's. So you can see here that there were only roughly 2% of the scores that were higher than Bob's. So you could say that Bob is in the top 3 percentile. You could look at that using the other inequality sign and say that Bob's test score is higher than 97% of the rest of the class, close to the 98th percentile. So again, it depends on how you're looking at it. If you're looking at it from the highest scores, you can say he's in the top roughly 2 percentile, or you could say that he scored higher than nearly 98% of the rest of the class. Now let's look at Bob's math test score. So again, we have a different situation, so we have to set it up for the situation that we're considering. So there was a mean of 70, so we changed the mean here to 70, and a standard deviation of 10, so we changed the standard deviation to 10, and Bob's test score was 80. So we changed this to 80 and click on compute, and it shows us that Bob scored better than 84% of the students in that class. We can change the arrow to the opposite direction, and it says that Bob is essentially in the top 16th percentile of the individuals who took that test. So you don't want to confuse the two and say that Bob's test score is higher than 16% of the students. You also don't want to confuse it the other way and say that Bob's test score is in the top 84%. Okay? So you want to make sure you don't get those two mixed up. Now let's consider areas under the normal curve. The accurate proportions or probabilities are found using programs and software just like we just did with StatCrunch. Approximations can be found relatively easily. If you divide up the distribution into the different standard deviation sections, and you know that they all add up to 100%, then you can find the relative proportions for each of those sections. So looking at this, you can see that about 34% of the scores are going to be between the mean and one standard deviation on the left, or the mean and one standard deviation on the right. And if you look at that as a whole, you can say that roughly 68%, which is just adding these two 34s, gives you roughly 68% of the data for a symmetric distribution are between -1 standard deviation and +1 standard deviation of the mean. Roughly 95% are between -2 and +2 standard deviations of the mean, and that is found by just going out here to -2 and going all the way up to +2, and just taking this 0.1359 and adding it to the 0.3413 and adding it to this 0.3413 and then adding it to that 0.1359, and it gives you about 95%. Then roughly 99.7% are between -3 and +3 standard deviations of the mean, and then again that's found by coming out here to -3 standard deviations and going all the way up to +3 standard deviations and finding the total area under the curve. And so that gives us general approximations. Now, what do we do about rounding? Because sometimes we get proportions or probabilities that have lots of digits to the right of the decimal. Well, my short answer would be there's really no need to do any rounding because that's the answer. You can just leave it as it is. A practitioner who is actually going to apply that result in practice can round, if necessary, how he or she wishes. But the answer is what the answer is. If you need to round, you should not round to shorter than the custom format for the type of data that you're working with. In fact, if you could, you should leave one digit beyond the custom format. So consider this first example. The mean number of students in Stat 101 each semester is 132.743. Okay? Now, even though a person is not you can't look at a partial of a person by using percentages or proportions, we're still considering computing a mean. And a mean is found by adding up all the numbers and dividing by the count. And that gives you sometimes a value that has decimals. It doesn't always give you a whole number. So when talking about the mean is actually not a whole number in this case. If you feel like you need to round that number, then you can round it, but you shouldn't round it to a whole number because the answer is referring to students, and the answer is somewhere in between 132 students and 133 students. So if you just round it to 133, then it's not entirely accurate. So what you want to do is round it a little beyond what you need. And so if we're talking about people are whole numbers, but we can round one outside of that and say essentially that it's somewhere between 132 and 133. And the practitioner can round that to a whole number if he or she chooses to do so. In this second example, the mean cost of utilities each month is in dollars and cents. That's how we pay. And so if the answer is 374.52934, you can leave it just like that, because that, in fact, is the mean cost of the utilities. We've taken all of the utilities for each month, added them all up, divided by the total number of months, and that's what we get. That is the mean cost of the utilities. If you must round, then we're dealing with dollars and cents, so you want to go one beyond what the dollars and cents is. So you could round this one to 374.529, which indicates that the amount spent on average for utilities is somewhere between 374.52 and 374.53. And if somebody who is actually applying this needs to round it to an exact penny, then you could, and it's not even going to be an exact penny, it would be an approximate, because exact has those extra decimal places, but the practitioner could round it to 374.53 if necessary. So it's never wrong to not round, to just leave it as is, unless you're specifically asked to round, then you would round. But if you're not, you could just copy the result from StatCrunch and paste it into the answer, and as is, that's the answer. One of the problems with rounding is that often students will round their answer. They had the correct answer to start off with, but then they rounded it, and they rounded it incorrectly, and because of the mathematical errors, they miss points. And so if you don't round it, you don't have to worry about that potential for making errors in your rounding. So it's always okay to not round unless you're specifically asked to, and there are problems sometimes with rounding that you might get the wrong answer. So now let's look at skewness, and in a distribution, skewness refers to a distribution curve not being symmetric. So when a distribution curve is skewed, it could be skewed either to the right or to the left. In this case, we have a positively skewed distribution because the skew is in the positive direction, or the tail in the skewed distribution, that tail is pointing to the right or the positive direction. So this could be called positively skewed or right skewed. Notice in a positively skewed distribution what effect that has on the mean and the median. Now the mean and the median are not in the same spot. When you have a positively skewed distribution, the mean is to the right of the median, and on this second graph we have a negatively skewed distribution or a left skewed distribution, and the mean is to the left of the median. So the mean is actually getting pulled in the direction of the skew by these outliers, because the mean is found by taking a sum of all of the values, including the outliers, and dividing by the total, whereas the median is only ranking the values at the end, and it's just finding where the middle number is. So it doesn't even care what the values are of the outliers, because it's only considering the middle numbers or middle number in the data. So in summary, the normal distribution is important to statistical analyses. It's used in a lot of the theory behind the methods that we use in this course. So it is helpful in that sense. But as you'll see in future sections, we don't rely on it too heavily. It works behind the scenes, so to speak. And that is the end of Chapter 6, the normal distribution.